Okay, there we go. Looks like I'm up. Hello everybody. It's April 14th. It's 8 a.m. Hope you are all doing well. So today I'm going to talk about some new some new convergence tests. Two of them today. One called the direct comparison test and one called the limit comparison test. But before I get to that, let me say something about sort of administrative stuff as relates to this class. I know you all did your midterm on last Friday, and I think that went very smoothly overall. I I haven't started grading them yet. I'll let you know when I get that done. Give me some time though, because it's already just Tuesday, and I'm like buried with stuff, not just for this class, but also for the school as a whole, some other service commitments that I have, and so I'm going to be very busy this week, but I'm going to try to get those done at some point. Okay. Today, you should know that your homework is due. This is homework number 7, as it happens. The number is not terribly important. But what I would like you to do is make sure that you submit your homework to your TA before the end of day today. The homework consists of 3 worksheets, worksheet 21, 22, and 23. So the way that you can submit that is by taking photos of your work, making sure that everything is labeled in a way that makes it very clear what problem you're doing when, and taking a photo of that, making sure the photo is not blurry, attaching that photo to an email, and then sending that email to your TA. And then your TA will grade it and hopefully respond to you with a score. Remember that homework and post-lecture slips together combined to be worth 16% of your grade, whereas of your post-corona grade rather, which ends up being 16% of your final grade, whereas your midterm and your final are worth merely 10%. Okay, so please keep that in mind when moving forward. All right. Let's see. Is there anything else I need to say? I don't think so. Oh, well, of course, there will be the post-lecture slip, which I will embed somewhere in the course of this lecture, let's hope, and I'll ask you to turn that in by, again, responding to the email that I sent you this morning. I sent you an email this morning at around 7 a.m., and if you respond to that with a photo of your post-lecture slip, I can respond to it, but then it will be sort of recorded and submitted properly. All right. Okay. So what have we been talking about? We've been talking about convergence tests. Remember what convergence tests are. Convergence tests are a way of, when you're given a series, an infinite series, it's a way of determining whether or not that series converges or diverges. Okay. And I know a lot of this is very new, and you might not understand why one would care about that question, and that's fine. We are doing all of this series stuff in the service of trying to get to a new representation of functions. Okay? And it's going to be very important for us to understand this question of convergence or divergence when it comes to this new representation of functions, because on the one hand, this new representation of functions is very powerful. It's called Taylor series. Taylor series are extremely powerful and give you great new insight into functions, which is what calculus is all about. But on the other hand, they have their own limitations, and it's important that we acknowledge that so that we don't abuse the power that Taylor series have in terms of giving us insight into functions. So I know even that might not be totally clear, but it's good to hear the words a little bit before you hit the concept super hard, just so that your brain gets a little bit marinated in the terminology and the vocabulary, and so that it doesn't come as a huge shock to you when we, again, start hitting it real hard, which we will do probably next week. Good. But today I do want to talk about some additional convergence tests, and these are called the comparison tests. There's two of them. Oh man, I can feel my arm being a problem. Okay, comparison tests. So the first one I want to talk about is the direct comparison test. I'll just put the And now listen, I know we've all seen this phrase direct comparison test previously, right? We've seen it in the context of improper integrals, right? When we talked about convergence tests of improper integrals, we talked about something called the direct comparison test, did we not? The idea was very simple. You had a function, one function which we might call f of x, and typically that was the one given to you. But you might just think of it, you have the function f of x, and then you have another function g of x. And their relationship is that they're both positive functions, but also that g of x is always greater than or equal to f of x. So you've got a bigger brother, g of x, and a little brother, f of x. And the fact is that if big brother has an integral, an improper integral, which converge, and remember we're talking about type 1 improper integral, whatever, those kinds of integrals for which the interval of integration was infinite, let's say on the right-hand endpoint went off to infinity. If you have an improper integral like that, which converge for the bigger brother, then it must be the case that the little brother also converged, right? You were able to make that deduction. And that was the DCT. And of course, if little brother diverged, then that would mean that big brother would also diverge, right? Now, we're going to see this same sort of structure for a statement which we're going to call the direct comparison test, which applies not to integrals, but rather to series. Okay. So how do we construct this statement here? So suppose we have two series. We have a sub n and b sub n. Now these are sequences, right? These are sequences of terms that will ultimately be put into, that we're ultimately going to take the sum of, all right? But these are sequences as of now. And the relationship is that we have a sub n here being little sister and b sub n here being big sister. So suppose that we have this sort of setup. Then, two things that we can conclude. If the sum, and I'm just going to write the infinite series like this, I'm not going to decorate it with any further decorations. You should understand that when I write this, I'm talking about an infinite series. If this thing converges, so big sister converges, then so does little sister. If big sister converges, then so does little sister. And just like the integral form of the DCT, if little sister diverges, then so does big sister. All right. So this is the DCT. We're going to see momentarily how this thing is used. Typically what you want to do, and this is by no means an easy task, but typically what you want to do is to have a sort of guess or a reasonable, how to say, like you want to have a reasonable sense maybe for whether a series that you're looking at converges or diverges, and then you use something like the DCT or what we're going to see soon, the LCT, to really justify that. Okay, and it's sort of a weird state of affairs in which you're kind of how can I say, you're kind of putting the cart before the horse. You're having to make a decision make a decision as to whether or not a series converges or diverges, and then based on that hunch or that guess, that decision, then use a argument to justify it. And I apologize that it's like that, but that's just the way it is, okay? I'm just going to be real with you. It's better to be perfectly honest with you about that somewhat uncomfortable fact, rather than you sort of having to, I don't know, struggle with the idea that, like, the DCT is not the kind of thing which you run the series through it and then you get your answer, right? You have to be a little bit creative about it. Because, for example, is your given series, if you're given a series, is it going to play the role of, is the sequence of terms of that series going to play the role of A sub n, or is it going to play the role of B sub n? Right? That's a decision that you have to make. And you make it based upon whether you believe that the series converges or diverges, right? Because if you believe that it converges, right, then you're going to have your given series play the role of A sub n. And then you are going to come up with a B sub n for which this first statement here holds, so that you can justify that the given series that you've been given is in fact convergent as per your sort of hunch. And similarly, if you believe that the given series that you're given is divergent, then you're going to exploit this second statement. And so what you want to do is make the conclusion of that statement, which is of this second statement, which is that this series here diverges. You want to make that statement apply to your given series. You see what I mean? So you're going to make the sequence of terms of your series, of your given series, B sub n. Hopefully that's clear. Let's see this in action, shall we? So, example. Sure. I think this works. The sum from n equals 1 to infinity of natural log of n over n. So, gosh, there's so many things that I can say, but maybe let's just take this problem. I have a hunch about this series. Okay, I have a hunch that this series here is divergent. And the reason that I believe that is the following. Natural log of n and n, both of those quantities, the one in the numerator, the one in the denominator, they both go to infinity as n gets larger and larger and larger. I think we can acknowledge that. But on the other hand, like if we were to try to use the divergence test, let's just think through this. Like, what if we were to try to use the divergence test? Will this tell us that this is divergent? Well, if we were to try to use the divergence test, remember what the condition there is. The condition is that we take the limit as n goes to infinity of the sequence of terms, and if that limit is anything other than 0, then we know that this is a divergent sequence. Oh, sorry, divergent series. Excuse me. So we can take the limit as n approaches infinity of this. And like I said, the issue here is that both the numerator and the denominator go to infinity. So this looks like a limit of the form infinity over infinity. So what we can do is use L'Hopital's rule. Now I'm going to play fast and loose with a L'Hopital's rule here. I'm going to pretend that I've found an interpolating function for this sequence, namely log x over x, and then I'm going to evaluate the limit of that real valued function. This is not exactly the same kind of object. This is a sequence. But we can apply the logic of L'Hopital's rule kind of if we think about, like, for example, taking the derivative of natural log of n by quote unquote taking the derivative with respect to n. Anyway, if that doesn't if none of this bothers you, that's fine. It really only bothers the the nerds in the audience who are more interested in who are very comfortable with abstractions and categories of, anyway, never mind. So what this is equal to by L'Hopital's rule is the limit as n approaches infinity of 1 over n over 1, right? So what have I done here? I've used L'Hopital's rule to take the derivative of log of n with respect to n to get 1 over n, and the derivative of n with respect to n to get 1. And what we see is that this is clearly 0. Okay? So what can we conclude by virtue of the divergence test, question mark? We can conclude nothing. Okay? Divergence test is a failure here. And the reason that it's a failure here is because the precondition that allows us to make any sort of deduction by virtue of this divergence test statement is that the limit of the sequence of terms is anything other than 0. But here we see for this series is definitely has a limit which is equal to 0. Okay, so that's bad. It's bad in the sense that we can't justify our hunch that this thing is divergent. And let me sort of go back a little bit and tell you why I believe this thing is divergent after doing this calculation. Okay, so we have log of n upstairs and we have n downstairs. Now they do both go to infinity, and that's good. And in fact, they go to infinity. How can I say? They both go to infinity, sure. But what I want to say is that log of n goes to infinity very, very, very slowly. This is a very important idea. Logarithms go to infinity extremely slowly, much slower than polynomial expressions like n. Okay, logarithms go to infinity slower than polynomials do. This kind of idea can be extended. Let me sort of give you on a separate piece of paper sort of a hierarchy of functions. This is important enough that I want to mention it because it'll be useful for you in your life. So probably the things which go to infinity, the things which go to infinity slowest are the things that never get to infinity. So we might call these things bounded functions. Okay, bounded functions go to infinity, not at all. So I guess we could in some sense say that they are the slowest in the race to infinity. Okay, so these are things like constant functions. These are things like trig functions and stuff like that. Okay, these are bounded functions. And what I want to say is they go to infinity much slower than something like polynomials. The next class I want to talk about, logarithms. This is another family of functions, and this is stuff like, natural log of x or log base, 15 of x, whatever. These logarithms, they do go to infinity, but they do so pretty damn slowly, okay? Now, I don't want to say that there's nothing in between these two family of functions. I just want you to, sort of have this general hierarchy in mind. Then we have, above logarithms, polynomials. These typically go to infinity, right? So this is things like x or x squared or x cubed, etc., or sums of them. And then, at the top, at least of this sort of scheme here, are the exponentials. Exponentials, so things like e to the x or 2 to the x. Okay, these go to infinity much, much faster than polynomials do. Polynomials go to infinity much faster than logarithms do, and logarithms go to infinity, whereas bounded functions don't do so at all. Later on, we will learn about things that are even faster in their pace to infinity than exponentials. Things like we'll learn about, factorials. But this is for another day. Okay, and the idea behind this hierarchy is that as we go through this chain here, I'll say it like this: these families of functions go to infinity faster as we sort of progress in this direction. Okay, this is a very important fact to have in mind. Okay, because when you're looking at something, where is the sheet of paper I was working on? Here. When you're looking at something like this, what you see is a logarithm upstairs and a polynomial downstairs. And the way you should think about it is that Well, the logarithm goes pretty dang slowly, right? And maybe it doesn't even really matter because it goes to infinity so slowly when compared to the n down here. Okay, so maybe this kind of resembles in your head something like 1 over n. I don't know. Right? Like you might as well replace this logarithm with something bounded if you want to. I don't know if that makes any sense. Okay, but this is a good good example to keep in mind. Now, divergence test failed us. How about another convergence test? What about, for example, the integral test? Integral test would absolutely destroy this problem, okay? And I want you to think about why. So in the integral test, what we know is that this series and this integral, these objects converge or diverge together, right? And what I want to say is that this integral here is very amenable to u substitution. Hopefully you all can see that. If you let u equal log of x, then you destroy this integral. Okay? What you will find, I believe, is that this u substitution will reveal that this integral diverges. It blows up. Okay? So integral test is definitely viable. But here's the way I want to do it. Finally, getting back to the DCT. The way that I want to do it is to use the DCT. Okay, and it's to make this insight that I was talking about before, which is that notice that 1 over n, okay, is less than or equal to natural log of n over n. Right? How do I know this? Well, the denominators are the same, right? So can't be the inequality can't be because of the denominator. But what we know is that natural log of n, as it gets larger and larger and larger, right, will eventually surpass 1 in value. Now, note that it doesn't happen at n equal to 2, right? The natural log of 2 is slightly less than 1. So this is only true if n is greater than or equal to, I don't know, 3. Then this equality is true. Because remember, log of e is being 2.7 something, log of e is 1. Right? So we need to pick numbers which are bigger than e in order for this inequality here to hold. Agreed? But is that technical fact that this inequality doesn't hold for n equal to 1 or 2, even though those are terms which are represented, you see, in this series? Is that important? No, because remember that finitely many terms can never have an effect on the convergence or divergence of an infinite series, right? What happens even with the first 5 billion terms of an infinite series has zero effect on the overall convergence or divergence of an infinite series. What you care about when it comes to the convergence or divergence of an infinite series is what's going on, and this is my sort of, this is maybe a thing which can spark your imagination, is what's going on in the neighborhood of infinity. Okay? For those infinitely many terms that are way out there, whose index is, cannot be captured by finite numbers, right? You're interested in the end behavior, in other words, of this infinite series. And you do not give a crap about what's going on with any number of finite terms here. So when it comes to something like the direct comparison test or the integral test, or as we're going to learn soon, the limit comparison test, any of the convergence tests, where you're only interested in the question of whether something converges or diverges, and not in the particular value that an infinite series might converge to, you never ever give a whit of care about finitely many terms. So the fact that this only holds for n greater than or equal to 3 is of no real importance to us. We don't care because it's only a finite number of exceptions. Now, if there were infinitely many exceptions to this inequality, then we would have to be worried. Okay? All right. Hopefully that's clear. So we know that 1 over n is less than or equal to the log n over n. So this means that according to this, we can use this second statement here. And if this is playing the role of a sub n here, 1 over n is, this is our a sub n, and this is our b sub n. Okay? And you can see that we do indeed satisfy this condition here. And so our conclusion is that if the sum of a sub n diverges, then the sum of b sub n diverges. Right? How do we know the sum of a sub n diverges, people? It's the most famous divergent series that there is. It's the harmonic series, yes? That thing is famously divergent, all right? So since the sum of 1 over n diverges, it's the motherfucking harmonic series, okay? It's the most famous divergent series that there is, okay? Since this thing diverges, the given series diverges. Is that clear to everybody? Are there any questions about this? Okay. Good. Let's do just one more example, a fast one, so that we can move on. How about this? This is probably a little bit more pedestrian. The sum from n equals, I don't know, 1 to infinity of, how about n minus 1 over, how about n squared plus n. Now, truth be told, if I was given, oh, and let's make this n cubed. Yeah, let's make it n cubed. This is important, very important. Truth be told, if I was given this problem, I would use LCT all day. And you don't know what LCT is yet, but maybe you have a sense of it because of of our work with integrals. This is an LCT all day kind of situation for me. But because we're talking about DCT right now, I'm going to kill this using DCT. All right. So first of all, what do we believe about this? Do we believe this is convergent or divergent? To me, it's very clear that it's convergent. And I hope that that intuition becomes clear to you. It's It's convergent because the numerator here is a polynomial, the denominator here is a polynomial, and when n is very, very large, polynomials are well approximated by their highest degree terms. So the upstairs looks like n, the downstairs looks like n cubed. Are you all following my logic here? When n is large, the upstairs looks like n, and downstairs look like n cubed. And so the quotient looks like 1 over n squared. And did you know that that's a p-series? And that's a p-series with p equal to 2. And that p equal to 2 p-series, therefore, converges because p is greater than or equal to 1. Now, I really like that logic there, right? Because that's me running through the precise reason why I believe this guy here is convergent. And in fact, that logic will be valuable for us to use. That kind of, maybe logic is not the right word, but that kind of argument is very valuable for us to use because we can implement it and make it useful for us in the context of the limit comparison test very directly, okay? All right, so, but let's use DCT here. So let's think about n minus 1 over n cubed plus 1. If we want to show that this thing here is, that this series here is a convergent one, then we want to be using this first statement of the DCT, the first one here. Because we want to be able to conclude that this guy here is convergent. We want this to be our a sub n. This to be our a sub n. And we want to come up with then a b sub n, which is bigger than it, which is bigger sister, right? Big sister to this a sub n. We want to find a big sister for this little sister. Okay, so what is something then that the alligator would prefer to eat over n minus 1 over n cubed plus n? Well, I think n over n cubed plus n. The alligator would rather eat that one. Why? Because what is the adjustment we've made in going from here to here? We've gotten rid of the minus 1, which is making the numerator smaller than n. We've gotten rid of it, right? So n minus 1 is obviously smaller than n, so this inequality holds. And by the way, well, whatever. Maybe I won't even mention it. And how can we make this even smaller now? Well, one way to make this, bigger. One way to make a fraction bigger is to make the denominator smaller, right? Smaller denominator means bigger overall fraction. So what we can do is rewrite this as n over n cubed. Yeah? And this is 1 over n squared. So then this is going to play the role of a sub n, and this is playing the role of b sub n. Okay. And so what we know is that since sum of 1 over n squared is a p-series with p equal to 2, which is strictly greater than 1, it converges. And since this sum here, sum of big sister converges, it must be the case that sum of little sister converges. Therefore, by DCT, the given series converges. Okay? Is that clear? All right. Let's move on now to the limit comparison test. Again, you've seen these words in the context of improper integrals, and there's going to be a version of this same statement, the same statement essentially, but now for series. Okay. So here's the statement. Suppose we have two sequences, a sub n, which is positive, and b sub n, which is positive. Okay. So this only applies for positive series. We'll deal with negative terms later. Suppose further that when we look at the limit as n approaches infinity of a sub n over b sub n, that this is equal to some number L, where L can be 0, a finite number, or a finite positive, infinity. So we're going to abuse notation a little bit in the usual way. We're going to pretend that this L here can be a stand-in for both a real number or this non-real object, this weird object that we're calling infinity. Okay? We know what it means. It means that this quotient here grows without bound. Okay? Then we can make one of three statements. There are three statements which are true. And the first is probably the most important statement. If L is positive. So if we're in this middle case here that I've described. If L is positive, then the sum of a sub n and the sum of b sub n converge or diverge together. And let me say, again, I'm going to emphasize this. This is the most important case of the LCT. It's the one we're going to use the most, by far. Second statement, if L is 0. So if L is 0, the way I would like you to think about it is that the relationship between a sub n and b sub n. So I guess what that means, that means that when n is getting very, very, very large, b sub n is much bigger than a sub n, right? It's getting bigger it must be bigger than a sub n in order for this quotient to be getting very, very close to 0, right? So you kind of think of that as being a situation in which b sub n, okay, is big brother. You think of that as being a situation where b sub n is big brother. And if big brother is convergent in it when we take the sum, then it must be the case that little brother is convergent. Okay? If L is equal to 0, then, and if, rather, the sum of big brother converges, then sum of a sub n converges. Okay? And third and final, if L is infinity. If L is infinity, then it's the opposite situation. B sub n is little brother now to a sub n's big brotherness, right? A sub n is getting big, while b sub n is staying relatively modest when compared to a sub n. And that's the only way in which the limit as n approaches infinity of this quotient could be equal to infinity. Is that clear? Now, if that's the case, then if little brother diverges, then big brother diverges. Okay? So those are the three statements that we can draw out of the limit comparison test. Are there any questions about that? So, if you recall, okay, so the typical setup is that you're given a series. And if you want to use the LCT, you're going to make the sequence of terms be a sub n. Then, you choose b sub n. You choose b sub n. Okay? And if you've chosen b sub n super well, then what you'll find is you'll fall into this first situation. Sometimes you have no choice but to look at the second and third situations, the second and third statements. But if you've chosen b sub n super well, then you'll fall into the first statement. Okay? How do you choose b sub n well? Here's how you do it. You think about what a sub n looks like when n is very, very large. So let me just say, typical use of LCT. Make your series, make this play the role of a sub n. Okay, that's the series that you're given. Typical use. Choose b sub n to be what a sub n looks like when n is very, very, very large. Okay. If you've chosen well, you will find that you will find L to be finite positive. And so you can conclude that the sum of a sub n and sum of b sub n converge and diverge together. Okay? So let's see this in action, shall we? If you recall our discussion about the integral, improper integrals, and the LCT in the context of improper integrals, what you will remember is that there I gave you very similar advice, right? We weren't using the letters a sub n and b sub n. We were using f of x and g of x, but I told you to choose g of x in such a way, I told you to choose g of x so that it looked like what f of x looked like when x was very, very large. So hopefully you see the parallel between these two statements. It's a very similar thing here. And what does this look like in practice? So suppose that you have the sum from n equals 1 to infinity of how about n plus 3 over the square root of n cubed plus 4n. Okay? I'm really just making things up. Now I have no idea. I'm pretty sure I have no. Yeah, I do not want to use the any other test. This thing is going to, it's. Sorry, let me slow down. I'm pretty sure that the sequence of terms here goes to 0, so the divergence test is not going to be useful. I don't want to integrate that thing, so I would rather not use the integral test. I don't like thinking about inequalities and like what's bigger or smaller than this guy, so I hate the DCT. I mean, let me just be honest. I hate the DCT. I hate it. If I can use the LCT, though, that's my go-to. I love the LCT. I think the LCT is very powerful. So I really badly want to use the LCT here. So what I'm going to do is I'm going to make this be my A sub n, and I'm going to choose B sub n to be the thing that this looks like when n is large. Now when n is large, because I have polynomial upstairs, that polynomial upstairs looks like its highest degree term, which is just n. And since I have a polynomial beneath the square root here in the denominator, when n is large, the thing in the denominator here looks like the square root of n cubed. The 4n does not matter. I can simplify this because I know algebra. Do you? So this is the same thing as n over n to the 3/2 power. Did you know that? God, I hope so. And of course, this is the same thing as 1 over n to the 1/2. Did you know that? If not, I'm not joking here. If not, you should go back and like learn or relearn, review rules of exponents. It's desperately important that you do that. Because, this is going to haunt you for the rest of your life if you suck with exponents, okay? Now, what am I going to do? I'm going to examine the limit as n goes to infinity of a sub n over b sub n. And I will bet my net worth that this is going to be equal to 1. Okay? I don't know. I haven't done the calculation, but I've done this enough. I've had enough experience around all of this that I know that this limit here, which is going to be playing the role of my L, is going to be equal to 1 on the nose. Let's just make sure that that's true. A sub n is this crazy guy. So I have n plus 3 over the square root of n cubed plus 4n. And I'm going to be multiplying this, or dividing it by b sub n, but that's the same thing as multiplying by n to the 1/2. Is that clear? Over 1, whatever. Right? This is the same thing as the limit as n goes to infinity of n to the 3/2 upstairs plus 3n to the 1/2. I'm just distributing, right? Divided by the square root of. Now what I'm going to do is factor out an n cubed from underneath this polynomial, from this polynomial underneath the square root. I can talk. And I get this. I can move this n cubed outside of the square root, but if I do that, I have to take the square root of it. And I can factor out, so what I'm going to do with the numerator is factor out an n to the 3/2. So I get 3, I believe 3 over n here. You should check that if that's, I'm pretty sure that's right. Now I'm going to move this n cubed outside the square root, and I'm again getting an n to the 3/2 and be left with a 1 plus 4n squared. So then as n goes to infinity, these terms die. You agree? And just by simple algebra, these terms kill each other. And so what I'm left with upstairs is 1, and what I'm left with downstairs is the square root of 1 in the limit. So this is equal to 1. And my net worth is preserved. Cool. So what does this mean? This means by LCT, the sum from n equals 1 to infinity of n plus 3 over the square root of n cubed plus 4n, and the sum from n equals 1 to infinity of 1 over n to the 1/2. So that's our b sub n, right? These two things converge or diverge together. But what do we know? We know the latter one. The latter means the second one. This one. Okay. We know that one. What? Does it converge or diverge? Which one? Which one? Which one is it? I think it diverges. What do you think? We know the latter diverges. Right? And so therefore, we know that the given series diverges. Is that clear? All right. So let's see. I've got 3 minutes or so. Are there any questions out there before? Are there any questions out there? Then let me just go ahead and give you the post-lecture slip. So post-lecture slip for today. We're gonna I'm gonna ask you to test the following for convergence. This will be question 1, because I will have a question 2. The question 2 will be, what are you confused about? And maybe I should apply the date. This is for April 14th. Okay. I want you to test the following object for convergence. The sum from n equals 1 to infinity of, how about the square root of n plus n squared plus 3 divided by 2n plus 5 to the 5th power. Am I hurting your feelings? Is this going to make you mad? Let's keep it. Let's do that. 2n plus 5 to the 6th power. Yeah, let's do that. How about it? Okay. So what I want you to do, again, is test this infinite series here for convergence. Tell me, that is to say, whether it converges or diverges, and give me a good argument as to why. You can use, of course, and I suggest that you use one of the tests that we learned today. I won't tell you which one I think you should use, but there's, I think, one that really is much better than the other for this problem. Today we learned about the DCT, and we learned about the LCT. These are both going to be important weapons in our repertoire of convergence tests that we will go on to use. And I hope that when you look at something like this, that this is like a gimme, okay? I swear, I know the answer to whether or not this converges or diverges, and I feel like I could give you an argument without even breaking a sweat at all. Just by looking at the structure of this thing, it's very clear to me whether or not this converges or diverges, and it's clear to me the approach that I would take as to why, okay? So please, try to work through this. I will, remember, your homework is due today. Don't forget about that. I will have worksheet number, I think it's 24. I will have that worksheet for you online today. And yeah, I think that's everything. And I'm finishing up here with 9 seconds to spare, so it worked out great. Hi, I love you all very much. I hope everybody is doing well and is doing safe. And I'll talk to you all next time. I'm going to open up a Zoom meeting right now for you to join. Oh, I forgot to give you the URL to that this morning in the email, I realized. Anyway, we'll figure it out, okay? Love you all. Talk to you soon. Bye.